Okay. Today we will study support vector machines and nonlinear transformations. So remember, in support vector machine we consider a binary classification. Our training set consists of n training points. Each xi is a point in Rd, which yi is -1 and +1. And we want to find a decision rule with the maximum classification margin. Now for this we have two formulations. There is a primal problem where we minimize half of W transpose W. So this was the objective, subject to Yn W transpose Xn plus B is greater than or equal to 1 for all n in 1 to n. So we have capital N constraints, one for each training point. W, where our variables are W, which is a d-dimensional vector, and the bias term, which is a scalar. We also have a dual problem where we minimize half of n going from 1 to n, m going from 1 to n, yn, ym, alpha n, alpha m, xn transpose xm minus the summation of alpha n, subject to one linear constraint, equality constraint, n going from 1 to n, alpha n, yn is 0, and all the variables alpha i's are non-negative. So in this dual formulation, our variables are these alpha variables. These are the dual variables, and there are n of them, one for each training point, and you have to minimize an objective function that looks like this. So this may look more complicated, but we saw last lecture that this is also a dual optimization problem, and it can also be solved using a quadratic solver. Today we will see the real reason why the dual formulation is so popular when we study nonlinear transformations. Now once we have solved the dual problem, we can find W as a summation of, so if alpha n star provides the optimal solution to the dual problem, then we can find W to be alpha n star yn xn, okay, where we sum over all xn, that is a support vector. So we saw this last lecture. And B, the bias term, is obtained by solving Ym W transpose Xm plus B equals 1 for a support vector Xm y. So just to remind you the structure of the solution, imagine you have a training points where you have some pluses like this and maybe some minuses like this. This is your training set. Then if you try to solve either the primal or the dual problem, you might get a solution that perhaps looks like this. Okay. So then there are 2 points that are close to the decision boundary. These two in this example are the support vectors. These are the points that are closest to the decision boundary. The plus is on one side of it, the minus is on the other side of it. You can think of a line like going on one side and the line that goes on the other side, and these 2 points will lie on the parallel lines. So these are the closest points, all others are further away. So if you remove any non-support vector point from the training set, it will not change the solution. You will still get the red line. The support vectors are the only one that determine the solutions, and for the support vectors, these are the only points where the alpha i's are positive, are strictly positive. For all other points, alpha i's are going to be 0. So if you remove them, it will not affect the solution of either W or P. One key advantage of this dual formulation is that the dual problem only depends on the data points x1 to xn through their inner products. That is through xi transpose xj only. So if you look at this dual problem carefully and look at how W and B are obtained, we do not have to actually directly deal with x1, x2 up to xn. All that matters is the inner products between xi and xj for any I and j. So let's look at it more carefully. So if you look at the objective function of the dual problem, the objective function is this: half n going from 1 to capital N, m going from 1 to capital N, yn ym, alpha n alpha m, xn transpose xm minus summation of n going from 1 to n alpha n. This is the objective. This only depends on the set through the inner products. Okay. So if I had just given you the inner products instead of the actual training points, you could still compute the objective function. Now look at the constraints. The constraints are saying that summation of alpha n, yn should be 0, and all the alpha i's are non-negative. Neither of them depend on the training points themselves. So if I had just given you the inner products of the pairwise inner products of all the training points, you did not have to know what the original vectors x1 to xn were to solve this problem. You can still solve it and compute alpha 1 star, the optimal solution. Once you have computed the optimal solution, your decision rule is of the form y equals sine w transpose x plus b. So here w is the solution to alpha n yn xn, or w is expressed like this, where we sum over all xn, that is a support vector, and b was obtained by solving ym w transpose xm plus b equals 1. So we solve this to get. Now the question is, does the decision rule only depend on the pairwise inner products, or do we need to know the actual values of the data vectors to compute the decision rule? What we have seen is, to compute the alpha stars, the optimal solution of the dual problem, we do not need the original data vectors. We only need the pairwise inner products between the data vectors. But perhaps to implement the decision rule, we may need the original data vectors. So let's see if this is the case. So we have seen that W is a summation of alpha n, y, and xn. So we'll substitute that in here, and then B is obtained by solving this quantity. So if we substitute, then y hat is going to be the sine of summation over xn, that is a support vector, which is the same as saying that alpha I for that quantity is not 0, of alpha n yn xn, now transpose, because we're transposing w, times the data vector x plus b. So the point is, this quantity also only depends on the inner product between xn and x. And similarly, b is obtained by solving this quantity by computing the pair, by if you only have the pairwise inner products, we can compute b as well. So why is all this useful? This seems like a somewhat interesting observation, but why is this useful? The point is, when you do nonlinear transformations, you may want to go in a very high dimensional space, and computing the original data vectors in this high dimensional space might not be computationally feasible. So let me do a simple example to explain why this observation can be useful. So imagine that we have an original data vector x, and we apply some nonlinear transformation z. So if you recall, one of the standard examples we had done before is, if you have, say, a data set that looks like this, and we want to draw a circle as our classification boundary, then what we will do is we'll transform z to, so this is x1, x2, then we'll set z to be maybe x1 square and x2 square, and then the data set suddenly becomes separable in the z space. So if we were to apply the SVM method in the z space, what do we need to do? We need to compute for the dual problem our objective function will be L of alpha is the summation of n going from 1 to n alpha n minus half of n going from 1 to n m going from 1 to n yn ym alpha m times zn transpose zm. What we did was we replaced the x with the z because we are in the z space, and we only need to have the inner products between zn and zm, and the other constraints remain the same because they did not depend on the data vectors. So the constraints we had was this, and the alpha i's are non-negative. Okay, so the dual problem, if you had to do a nonlinear transformation, the only change that would happen was to replace xn transpose xm with zn transpose zm. And so if the inner products zn transpose zm are easy to compute, then the complexity of nonlinear transformations is essentially unchanged. So this is attractive because it allows us, if there is an easy way to compute inner products, we can go to very high dimensional spaces and we can apply the support vector machine method in high dimensional spaces. So one way that allows us to do easy computation of the inner products is something called a kernel method. Okay. So what are kernel methods? Let's consider a simple example. Let's say our data vector has 2 points, x1 and x2. And we apply a nonlinear transformation to z, and we get 1. We want to do a second order transformation, but we want to keep all the terms. So we have the product term between x1, x2, x1 square, x2 square, and the first order terms. Now, if we were to compute, say, z transpose z prime, so we have another vector, say z prime, which is 1, x1 prime, x2 prime, x1 prime square, x2 prime square, x1 prime, x2 prime. So x prime here is x1 prime and x2 prime. We are transforming both of them. And if we compute z transpose z prime, this will be 1 plus x1 x1 prime plus x2 x2 prime plus x1 square x1 prime square plus x2 square x2 prime square plus x1 x2 x1 prime x2 prime. Okay. So the thing is, in order to compute z transpose z prime in a straightforward way, we would have to first compute z and z prime. That involves like taking the two terms into 6 terms, like mapping x1 x2, the two variables, into 6 of them to compute z, and similarly mapping x prime to z prime and computing inner product. So the direct complexity of computing this inner product will scale with with the length of z. The longer z is, the more terms we have to compute. However, the question is, can we compute z and z prime, or actually the inner product between z and z prime, directly without first computing z and z primes separately? And the answer is a yes, using a method called kernel trick. So the idea behind the kernel trick is the following. We know that z and z prime are second order transformations of x and x prime. So let's define a kernel function like this. Let's take the inner product between x and x prime, that is in for the original vectors which are smaller. We compute the inner product, add 1 to it and square it. So what do we get? This is 1 plus x1 x1 prime plus x2 prime square. So if we expand this, we get 1 plus x1 square x1 prime square plus x2 square x2 prime square plus 2 x1 prime plus 2 x2 prime plus 2 x1 prime x2 prime. So if we compare this, so this is fairly easy to compute. We just had to take the inner product between the x vectors and then square it. If you compute this quantity with what we have here, it looks very similar. The first 3 terms are the same, or the first 4 terms are the same. However, there is a factor of 2 in 3 of the terms. So we have a factor of 2 here, but we don't have a factor of 2, say, in front of this term, in front of this term, and in front of this term. There's a factor of 1 here, whereas we have a factor of 2 in this expression, but we have 1 in front of the remaining terms. So it turns out that the two are essentially identical if we had defined the z and z prime slightly differently. So this quantity so if we had this term, but we put in just a square root 2 here, and z prime to be 1, I should not have this square here. Should have the square at both places. x2 prime square root 2 x1 prime root 2 x2 prime root 2 x1 prime x2 prime. If z and z prime were these vectors, then their inner product was exactly 1 plus x transpose x prime square. And note that there is no real difference between defining z this way and the original way. They will lead to the same solution because the constant factors of square root of 2 will not make any difference. So we have now found a simple way to compute the inner products without having to explicitly compute z and z prime and then take the inner products. The right hand side provides a simple way to compute the inner products for the quadratic transformation without having to compute z and z prime. We can directly compute the inner products from the x vectors themselves without having to compute the data vectors z and z prime first. And this actually has important consequences when we consider more complex transformations.